Even though the output of our mapping with known poses node is already impressive, there is still room for improvement. In this lesson, we will study the theory and the mathematics that we need to transition from creating a simple occupancy grid like the one on the left, which our nodes currently generates, to create a probabilistic occupancy grid like the one on the right. The difference lies in the fact that currently our mapping with known poses node directly uses laser data to generate the grid. If a laser scan indicates that that cell is occupied, we mark it black, otherwise we mark it white, so as a free cell. However, what happens when the laser provides a conflicting information about the state of a cell? For example, one scan might indicate that a cell is free, and the next one, due to inevitable noise that is affecting the laser, might indicate that the same cell is occupied. In this case, as clearly seen in the highlighted region of the map data is overwritten. If a LiDAR reading identifies an obstacle, the corresponding cell is marked in black, and if the following scan detects no obstacle in the same cell is overwritten and is marked as free. This isn't a very smart approach, because it might be that the first scan told us the truth, and the second one did not. But generally speaking, how do we combine multiple, possibly conflicting LiDAR readings? How do we know which one is correct? Once again, the answer lies in mathematics, or more precisely, in probability theory. So far, we have approached the mapping with known process problem with boldness, assuming that we could extract the perfect map of the environment M. Thus, we associated a value in the occupancy grid with each laser scan that was either 100 to indicate that that cell was definitely occupied, or 0 to indicate that that cell was definitely empty. In reality, as you may have guessed by now, in robotics and in self-driving, we rarely deal with certainties. Therefore, rather than creating a certain map of the environment, we want the most likely one, namely, we want the best representation of the environment, the most likely, based on the available data. The probability associated with this map is determined by how the robot has moved over time, thus from all the poses of the robot over time, so the variable x1 to t, and from all the measurement that the LiDAR has collected over time, thus the variable z1 to t. This probability indicates the overall probability of the map, but since the map is composed of a certain number of cells, the probability associated with the map is simply given by the product of the probabilities associated with each cell. In this case, with the variable mi, we indicate the probability of the cell I of the map of being occupied. Clearly, this probability depends on how the robot has moved, thus on which areas of the map it has visited, and also from the LiDAR readings. Here things start to get a bit complicated and complex mathematical equations come into play using tools from probability theory such as Bayes' theorem. Since deriving these equations is not essential for the purpose of this lesson, we can simply assume that with a bit of black magic, our mathematician friends have provided us, our robotic software developers, with this equation where they have decomposed into three terms the initial equation, so the probability of the cell I of being occupied as a function of the LiDAR readings, so the variable z1 to t, and the robot pose, so the variable x1 to t. If you are interested in the mathematical details of this derivation, you can find these equations along with their explanation in the PDF that is attached to this lesson. Let's clean up a bit in order to try to understand what each term of this equation tells us. The first element can be read as the probability of the cell I of being occupied, based uniquely on the current position of the robot and the current LiDAR reading. But this is exactly the sensor model, which we have already developed within our code. With the LiDAR model, in the previous lesson in fact, we associated a number with each cell that was 0 or 100, depending uniquely on the current position of the robot and the current sensor readings. The second term, on the other hand, can be read as the probability of the cell I of being occupied on all the robot's previous poses and all the LiDAR readings previous to the current one. This indicates a recursive term, so the probability that that cell had of being occupied before the current iteration. This term takes into account all the previous sensor reading, thus considering whether the LiDAR had already observed that same cell and which value it associated. Finally, the last term simply indicates an initial probability of the map, so the default value that we assign to each cell when it has not yet been observed and therefore its status is still unknown. After all, creating a probabilistic map of the environment isn't that difficult. We already have all the three elementary components for this calculation and we just need to combine them. To simplify this calculation, when we implement this logic within our robot software in the upcoming lesson, our mathematician friends provides us with another tool in order to easily work with probabilities and facilitate calculation. This tool is called log odds notation. Simply put, this tool will allow us to express probabilities in logarithmic form and vice versa. The advantage is that with this new notation, our equation no longer looks so scary, and it becomes more readable and also more intuitive to understand the meaning of each term and how they should be composed to obtain the overall probability of a certain cell being occupied following several LiDAR readings taken at different positions of the robot.